Now that we talk about how to calculate the pH of acids and bases, we want to bring up this relationship between Ka and Kb for a conjugate acid-base pair. So to start with this, I want to ask you to think about a weak acid and its conjugate base. So weak acid in this case has a generic formula of HA, and its conjugate base, of course, is A minus, right? Let's write their reaction in water. So the HA reaction should be pretty familiar to you. That's the HA plus water forming hydronium and A minus. And of course, the K of this is what we call Ka of HA. Right? It's the Ka of that weak acid. Now, the conjugate base, when it reacts with water, it's going to accept a proton, so it forms HA and then also produce OH minus. That K is what we call the Kb of A minus, the conjugate base. Something interesting happens when you add these two reactions together. The HA cancels, the A minus cancel, and we end up getting H2O plus H2O forming H3O plus OH minus. Now the K is of course going to be the product of the K of the two reactions, right? Remember that when you add reactions, the K gets multiplied. So in other words, the K here is going to be Ka of HA times Kb of A minus. But the K of this reaction should be familiar to you because this is none other than your autoionization of water reaction. So therefore the K itself is Kw. So in other words, we just found this new relationship that Kw is the same as Ka of an acid times the Kb of its conjugate base. Now we're going to do the same derivation that we did when we look at base calculation. We're going to take the negative log of both sides of the equation. If we do that without going to the details here, we end up getting pKw equals to pKa plus pKb. Again, that operator p just means negative log. And then at 25 Celsius, pKa plus pKb is 14. What this is telling you is that if I know Ka of an acid, I can calculate the Kb of its conjugate base. If I know the Kb of a weak base, I can calculate the Ka of its conjugate acid. Okay, here's a problem to show you how that works. It says calculate the Kb of the acetate ion. Acetate is this formula. If you look up the Kb value in the Kb table, acetate is not your standard base that would be listed there, but know that acetate is the conjugate base of acetic acid, which has that formula, and we have Ka value of acetic acid. That's in the Ka table. It's 1.8 times 10 to the minus 5. So now, with this new formula, which is Kw equals Ka of an acid times Kb of its conjugate base, we can calculate the Kb of acetate by just taking Kw divided by the Ka of acetic acid. We use these two numbers here. We find the Kb of acetate to be 5.56 times 10 to the minus 10. This just opens up a whole universe of values. So notice that we have Kb values here. You see how they got all these Ka values? It's really just using that formula that I just showed you. And then if we scroll back way up to our Ka table, where we have all these Ka values right here, now we're able to also calculate the Kb for all of these conjugate bases, which has no numbers right now, but now we can calculate. Okay, we have now learned how to calculate pH of acids, bases, and we also know that we can use the properties of these acids and bases in water to connect them together so that we can calculate Ka and Kb of any conjugate acid-base pair relationship. Now, we're going to bring everything together and combine them in the form of salt. And salt, as you may remember from Chem 11, is just another name for ionic compound. In this section, we specifically are going to consider only soluble salts, which means that when you take these compounds and you put them in water, they're going to dissociate completely to form two things, cation and anion. Acid-base property of these salts will depend on the acid-base properties of the ion that make up the salt, which hopefully will make sense, right? So in order for us to understand whether a salt is acidic or basic or neutral, we're going to need to know what kind of cations and what kind of anions make up the salt. We're going to start our discussion by looking at cations. So there's really two types of cations you can have. You can either have a neutral cation or you can have an acidic cation. A neutral cation are cations that combine with hydroxides to make the strong bases. So these are your group 1 cations and some of the group 2 cations. We had mentioned this when we discussed bases. These are lithium, sodium, potassium, rubidium, cesium, and francium, and then calcium, strontium, and barium for the group 2. So those are it. Those are all neutral. So if you put them in water, they don't change pH at all. They just float around, spectator ions. They don't do anything. But with the acidic cation, they actually change pH. They lower the pH when you're dissolving them in water because they can actually dose donate protons somehow or act as a Lewis acid. So in this case, we have two different types. The first type is type we call the conjugate acid of a weak base. Okay, so what are conjugate acid of weak bases? Now you have to think about what weak bases are. It would be from that KB table. So methylamine, pyridine, ammonia, these are weak bases. Their conjugate acid will be weakly acidic. They're going to have some Ka value associated with it. So for ammonia, the conjugate acid is ammonium. With methyl ammonia, the conjugate acid is methyl ammonium ion, which is CH3NH3 plus. And then for pyridine, conjugate acid is the pyridinium ion, which is C5H5NH plus. So all of those is going to be weakly acidic, and therefore if you have them in water, they're going to change your pH to the downside. The other type of ion that's going to be acidic are these small highly charged metal ion. Now for this, you're going to have to go back to one of our earlier lectures on acid-base chemistry, where we show that these highly charged metal cation, usually the transition metal cation, they are able to accept electrons. And of course, when something can accept electrons, we call them Lewis acid. And then once they accept electrons, they form this coordinate covalent bond. And then in water, these complexes then act as Bronsted acids. They can actually donate protons. So again, if you don't remember this, you might want to look back at one of the earlier videos where I was discussing Lewis acid. So examples of the cations would be things like aluminum, iron, zinc, copper. Really, many of the transition metal cations will be able to do this. Now we're going to go after the cation to the anion. So like cation, anion from types, there's the neutral one, and then there's the basic one. Anions don't tend to have acidic properties. Cations don't tend to have basic properties. So with anions, we just have neutral and basic. The neutral anions are the conjugate base of strong acids. So remember that we had a list of strong acid at the very top of our Ka table. The ions, the counter ions, the conjugate bases of those strong acids can't really perform a base function when water is present because water is a stronger base. So as a result, all of them are neutral ions. So these are chloride, bromide, iodide, nitrate, and perchlorate ion. Okay, we also have some basic anions, and these are the conjugate base of weak acids. We have a lot of weak acids in our Ka table, right? Anything below hydronium is a weak acid. So just some examples of weak acids are HF, acetic acid, H2HCO2, HNO2, right? Nitrous acid, carbonic acid. So the conjugate base of all of these acids are basic. They're weakly basic. So therefore, they all have the ability to change pH. So these are their conjugate bases, right? So when you have one of those ions as your anion, then it's going to influence the pH of the solution. The third category of ions that I didn't put as cations or anions is amphoteric ions. They can act as acid or base. We had discussed this before in an earlier video. So if we want to know what the amphoteric ion will do, what we need to do is compare its Ka value to its Kb value. So whichever value is larger, that's what the ion will do. For example, let's look at the bicarbonate ion, which is HCO3 minus. You can potentially write two different reactions with bicarbonate. One is bicarbonate acting as an acid, which means it's donating protons. So if it gives away proton to water, it's going to form H3O plus carbonate. And the K for this would just be the Ka of bicarbonate, and you can look it up. It's in the Ka table. Now, bicarbonate can also accept proton from water. So now it's the opposite. The water acts as an acid, gives the proton to bicarbonate. Bicarbonate forms carbonic acid and hydroxide, so it's a base reaction. K for this would then be called Kb of bicarbonate. So you see that the bicarbonate ion can have both Ka and Kb. If I look up the Ka value of bicarbonate, it's actually 4.7 times 10 to the minus 11, and then now I need to find the Kb value. The Kb value is not given, but we can calculate it using that Kw and Ka relationship. So in this case, we will take Kw divided by the Ka of the conjugate acid being carbonic acid. So we'll use the value of Ka of carbonic acid. Very important, I'm not using this Ka, which is the Ka of bicarbonate. I'm using the Ka of carbonic acid, which is this number. So it's different. What I end up getting is this value. So what I'm comparing is these two numbers right here. I'm comparing the Ka of bicarbonate with the Kb of bicarbonate. The Kb is larger, so therefore bicarbonate would act as a base. So it's a basic anion. Not every anion is going to do that, so it really depends on the anion you're approaching. So I'm just stating here that if you're doing exactly the same work that I just did for bicarbonate on the bisulfate ion, HSO4 minus, you'll find that this ion is actually acidic. because its Ka is larger than its Kb. So you want to go ahead and do that on your own and prove to yourself that that is indeed an acidic ion. So you have to be able to do that with any amphiprotic ions you have. Another situation that is a little complicated for salt when you have both acidic cation and a basic anion. So you have two things, both of which will change pH. So how would you figure out whether your salt is acidic or basic? The way you will figure this out is you're going to have to compare the Ka of the cation with the Kb of the anion. Whichever number is larger, then that would determine the property of the salt. So for example, let's take a look at this salt. It's called methyl ammonium sulfide. It has the formula CH3NH32SO3. The salt dissociate into two products, methyl ammonium ion, which is CH3NH3 plus, and sulfide, which is SO3 2 minus. And again, that cation is something that is the conjugate acid of this weak base, methyl ammonia. And I want to emphasize again the importance of you recognizing some of these formulas from the weak bases. Remember, they're all derivatives of ammonia. Anytime you have an N there that's substituted, you really want to be able to recognize that they're weak base. Okay, so and then, of course, the conjugate acids of those weak bases. So in this case, methyl ammonium is the conjugate acid of methyl ammonia, which is a weak base. So this is an acidic cation, and you can calculate the Ka. So if you know the Kb of methyl ammonia, you can just use Kw over Ka. But that table that I just showed you with the weak bases, they already calculate the Ka for you. And that's 2.3 times 10 to the minus 11 for the Ka of that conjugate acid. And now sulfite is the conjugate base of a weak acid. The weak acid here being the bisulfite ion, HSO3 minus, or the hydrogen sulfide ion. So therefore, sulfite is a basic anion, which means it has the ability to accept proton. We have to calculate its Kb, and we can do that by using Kw. Kb here is going to be Kw over the Ka of the bisulfite. You can find that number in your Ka table, but when you calculate it, you'll get 1.6 times 10 to the minus 7. So the two numbers you're comparing here is this and that. And you see that the Kb value is bigger than the Ka value. Since the Kb is bigger, therefore the anion will dominate. So the salt is basic. So again, think through this discussion because it is a little bit more complex than just the standard acid or base because you have both of them in there. You have to think through what's present, what's the cation, what's the anion, what each one of them does, and then combine the property to predict for the salt.